So we continue. So this is the attention layer. This is the recurrent model of attention, as introduced in Badan newspaper. Well, it has been widely used, guys. Attention layer, I mean, found its place in many of the applications. So, sorry. Attention took very, attention from the scientific field, because it helped people further model longer sequences. So from vanilla RNN to gated models, that was a step to model recurrent models, sequence models. And this was another step. So with the help of this mechanism, we could define or just model longer and longer dependencies. And this attention mechanism brought another discussion. So it is about the relation of the input to the output. So actually we are trying to just make a mapping from the sequence to sequence, but actually this is the first time we are trying to map those things between each other, which in a transparent way, because previously any model, LSTM, single or decoder to encoder, encoder to decoder, we didn't know their relation. It was not transparent. So actually, I think this attracted this idea attracted attention for the scientists of the field, and there came the transformers. Guys, transformers today is the de facto standard of neural NLP, and it's a very powerful tool. We still don't know how strong it is because we are trying to apply it as the humanity to many fields. Today's Google search, Amazon search, they all use a version that is created from the transformers, which is called BERT, B-E-R-T. You've heard of it. I'm going to get there. And actually, that thing that happened like 6 months ago, do you remember it? There was an article in Guardian written all by an NLP engine, which is called the GPT-3. Actually, GPT is also a transformer, a version of a transformer, which was created from a transformer. It includes a transformer. And if you haven't read the article, I strongly recommend you go and read the article, because it's about why shouldn't be scared of robots, written by the robot. And after I read it, I was really scared of it, guys. I mean, it really makes you scared because he talks very logical and he makes really sense. And you feel like there is something in it, guys. Let's not believe it kind of feeling. Please read it. It's a fantastic paper. So it's very famous. I'm sure you've seen it. So the paper that introduced the idea of transformers was called Attention is All You Need. So it is like a charming title. Attention is all you need. Like humans need attention, kind of. But what the title was trying to say, wait for it, the attention that was defined by Badan's paper, the recurrent model of attention, is actually nice. But it is only the attention we need. We don't need the recurrent model, it says. And very strangely, transformers do not include a recurrent model, guys. So it's a bit funny to say this because the course is called Recurrent Neural Networks. And the recurrent neural network literature just led us to a point where the best architecture for neural language processing, I'm not saying this is the best architecture for example, for the control system example, I'm going to discuss it in the following slides, is for neural architecture is something that is not recurrent. So attention is all you need is like, and the title has many meanings because it's the transformer architecture is totally based on attention, but it doesn't have a recurrent part. So you don't need recurrency. Attention is all you need, is the idea of the title actually. Okay, let's get to what transformers are. The name is so cool, isn't it? I mean, transformers. I don't know you guys, but for me and Salih Hoca, transformers was something very powerful. I mean, forget the new movies about transformers. Transformers was like 20 or 30 years ago, was the single epic scientific thing, because there are lots of things today. There are lots of series, TV series, and Netflix, but it was one of the most important things. And because By the way, it's much older. It's much, the cartoons are much older. Whatever, so the name is cool in my opinion. Whatever. The intuition of the transform. So before I get to the details of the architecture, I'll try to introduce you what transformers are and what is the intuition. Then I'm going to get briefly into the architecture. And after I finish that brief introduction to the architecture, I'm going to guide you to sources there which you can find the detail of the architecture. Before that, let's get the idea. Encoder-decoder architectures with the current model of attention was good. But one downside was you had to feed the sentence and get the output. It was like a string. So it was just feeding the word, the sentence, and getting the output. So you couldn't parallelize the option. So for long sentences, you needed to wait longer, just like a translator does. However, with transformer, we get the complete sentence. We process it in general, so in parallel, all words in parallel, because we feed the words as sequence serial, and we get the total output in one breath, a couple of breaths actually, but in one breath. So the most important part is it is not recurrent. Although it gets varying length input, it can process it. Actually, it doesn't get varying length input, but it tricks itself to get varying length input. And it does it all together, just like a CNN does. But it can process sequences because it embeds the input in a way that it can process sequences. We're going to get to the nice parts of transformers. So one of the main characteristics of RNN is the input and output sequences are processed sequentially, but in transformers, this is not the case, guys. Okay. So transformers were efficient compared to LSTMs, and this efficiency helped its training as well. So that sequential manner was one of the biggest obstacles of difficulties in training those systems. So if you don't have a sequential system like LSTM, which is a deep neural network with the length of the sequence length, depth of the sequence length when it's unrolled in time, this is not the case. You have a solid architecture. So what is this solid architecture? So as we'll see in the case of the concept of the transformer architecture, it is RNNs are completely removed. I mean, that's surprising. I mean, when you first hear about transformers and then people say there are no RNNs in it, it's a bit startling because up to transformers, you will be studying, you have been studying RNNs and how fantastic they are, all LSTMs, including decoders. And at some point, okay, you don't need RNNs, but why and how? I just stop. Actually, it is efficient for some problems, but it is efficient for those problems, still very surprising. So the ability of the transformers to enormously parallelize to get all the sequence all together allowed it to train larger models. And with those larger models, it could do larger things, and there was a larger capacity. And actually, that guy who wrote the article saying that we shouldn't be afraid of robots used billions of parameters, hundreds of billions of parameters, guys. This is not possible for a case of LSTMs and stuff. You won't be able to train it. So you could just, when you don't have the RNN inside the machine, it is easier to train. And such models were unthinkable before transformers. Okay, so transformers are revolutions, and actually it is very fantastic. And it's not sequential. So how come it works? This is an unfinished sentence, whatever. The transformer architecture is highly complex, let's say. Let's finish it that way. It is, again, compounded by encoder and a decoder. But none of them are recurrent neural networks, guys. Actually, they have some components which are related to attention and decision. I'm going to briefly get to those parts, but I'm not going to get into details. And in the original model, all inputs had an embedding layer of the dimension of 512, which means you can feed a sequence of up to 512 And actually, if you fed something smaller than the length of 512, actually that is the length of the sentence, the input sentence to be translated, if this transformer is a translator. Okay? If this is shorter, which is usually the case, you never construct those that much long sentences, just left them blanks. So the input to a transformer is something like this, guys. Let me show you. Because that was the trick he pulled. Abi gene masum kayboldu ya. Delireceğim ya. Masum niye kayboluyor ya? Allah Allah. Sorry guys. Because tabii ki bu yüzden. Gene masum kayboldu. Allah'ım ya. Buldum. Okay. Mouse cursor'ımı göremiyorum da o yüzden arkadaşlar. So if you had a sentence of 4 length, for example, the first word, the second word, the third word, the fourth word, they're all embeddings, some sort of word-to-vec embedding. So it's a vector, it's a vector, it's a vector, it's a vector. So in the end, you have an end of sentence embedding, and the rest is empty up to 512. Hayır, zaten buraya yazıyorum. Bir cursor iyice zorlaştı ya. Neyse şimdi şunu bir kapatmamız lazım. Cursor'sı arkadaşlar, kusura bakmayın. Clear. All drawings. Okay, I got it. Okay, so this is how you feed it. So you cannot feed something larger than 512, but that's the first version. You can enlarge it. They are fed to something called the input embedding. Input embedding is a kind of word-to-vec. I mean, I don't know which one they've studied. But the embedding is not only the input embedding, guys. They have an additional embedding factor, which is called the positional embedding. And they pull a very nice mathematical trick, which I'm not going to get into the details of. They pull a trigonometric trick for the indices of each sequence. For example, you have sent a word, a sentence, the first word, second word, third word. The index of the first word is 1, the index of the second word is 2, the index of the third word is 4, 5, 6, whatever. You calculate a cosine sine-based number, and you add it to your vector as well. This way, you add the information of the order in the sentence. So it is not only the value, but that addition shows that it is the first word in the sentence, the second word in the sentence, the third word in the sentence. So when you're feeding it, you're actually embedding the order information inside as well. You have to do this because for an LSTM, you are feeding the input sequentially. You're feeding the input now in parallel. So and at this feed-forward network, which is a fully connected network, everything is connected to everything. That order will be lost. In order not to lose it, the guys embedded that information with a positional encoding idea. So in addition to regular word-to-vec encoding, they have added this positional encoding stuff by just some adding. And so it is like you're creating a value for each word depending on their order using a trigonometric function, and you're adding each embeddings for each word. So you create an embedding for the words, which represents the similarity of the words plus the order of the words in the sentence. So that's the input embedding, guys. Good. I continue if you have any questions. So I'm focusing on the encoder. The encoder part after the embedding is composed of two main parts. The first part and the second part. This is the first part, I'm sorry. First part and second part. The first part is an attention part. It calculates a self-attention. A self-attention is the distance or similarity of each word in the input sequence. It creates this self-attention because it tries to understand the relation of each word within the sequence. Because when you're constructing a sentence, sometimes the word at the beginning is very much related to the word in the end, in meaning sense, okay? And the self-attention mechanism creates that relation. And it doesn't create that relation in a single dimension. It creates a number of different self-attention similarities. So it is like in one dimension, word 2 and 3 are related. In another dimension, word 4 and 5 is related. In that other dimension, word 1 is related to another word. There's a very nice figure indicating that. Actually, I'm going to show it to you. So guys, this is the self-attention. So imagine n is equal to 6 because it was the implementation in the original transformer, guys. And I indicate each of them as some separate spaces. So actually more is related to making. In this line is gray. Can you see that is gray? In this gray dimension, guys. Okay? And making word is related to this word in this brown dimension. So making is related to more and making is related to difficult in different self-attention dimensions. It is like each dimension of attention carries another concept of the language. One carries the concept of time, one carries the concept of place, one carries the concept of the, I don't know, something else. So making more, so this gray dimension carries the intensity of the actions, and the brown one carries the, I know, vector of the actions, so difficult, making what? Or so as you can see, making, this is pink, the purple one being the self-attention, which is the word itself. So actually by defining different attention mechanisms, you are creating different meaning dimensions, because the relation between two words in a sentence, in a single sentence, can have different concepts. So you're creating different dimensions of concepts. And you're encoding this input sentence in that dimension of concepts. Any questions? Because that's a very difficult thing to understand. That was their idea. It's a bit confusing. This is called the multi-head self-attention. So each head like representing a concept of attention. And in multi-dimensions, multi-heads, we are defining the relation between each word in the sequence. So how come does it work? So this guy has some weights, this guy has some weights, and it creates those weights. So it was trained to create those different dimensions of concepts inside the sequence. So actually we are designing the entire image with the relations of the words of different types of relations defined in 6 dimensions. This n can change. So actually the number n, sorry, let me make it, number n actually designates your different types of similarities inside the input sentence. Okay? That's what it calculates. Then it is being fed to a fully connected layer. Those all relations are being just multiplied in each other to create a convolved meaning out of everything. And at this point, actually, you have the representation, just like the recurrent encoder does. And when you feed this, and you have this, you have a high-level representation of the entire sentence in a single click. You have fed the entire sentence, you had one click, you had this, regardless of the length of the sentence. And actually, today's Google plus Amazon search, and Google announces it, this is fact, and Amazon does not announce it, but my friends work in Amazon, and I asked them, they use this encoder, BERT, B-E-R-T, this encoder-based feature extractor for Google and Amazon. And they say, Google research and Amazon research say that it was a revolution as well. After they started to use the encoder of the transformer, the searches were much better, because when you were writing something, it was much faster, because as you write it, just single sentence, you get the result. And it is a much better system that you can train, because it's not recurrent. You can train whatever you want. Okay, no RNN, yes, no. The key aspect is the self-attention mechanism, different from CNNs and RNNs. What you first model is the attention inside the input sequence. So for many applications, it is replacing the RNNs. Is it better? For some applications, because it's efficient, it is more trainable, and it's more trainable, it is better. So I want to say it's better, it's efficient. This makes it better in many applications. So in language translation, this is the case, because we provide a sentence in one click. So it is not a modeler, guys. It does not model. Of course it models, it's a mathematical function that models, but it does not model a sequence modeler. It's a transformer. I should have said it is not a sequence modeler. It's not a sequence modeler. It is a transformer. It transforms. Good. So is this the right idea for languages? Apparently so. I mean, this is a very nice discussion about transformers, is because when the order of the language changes, sometimes we understand. I mean, okay, order carries meanings, and there's this positional encoding to indicate that meaning, but still, the order is flexible in a language. And we know this for a fact. When I say reverse sentences, you understand it. However, the more important thing about the language is the types of relation the input sentences, input words in the sentence have, and how are you going to reconstruct that relation in the output sentence. And that's why in the decoder, we have another attention mechanism. Okay? We have both the self-attention and encoder-decoder attention. So actually the input from the encoder comes, İnşallah gene yok olmayacak ya şeyim. Hadi bakalım deneyelim şansımızı. Evet. Yes. So it yok oldu. So it comes from here, guys. So it comes from here. So the encoder output comes here and it enters here. This is where the attention of the encoder's output is calculated to the output of the decoder. And it's gone here. So it's gone here. And it's fed back to itself. So actually, the operation of the decoder is a bit sequential. So the slower part of is the decoder. And the first step of the decoder is this part, is again a self-attention mechanism in which the decoder calculates the similarities between its created words so that it can construct a meaningful sentence. So the whole architecture is about attention, guys. So that's why the paper is called All You Need Is Attention. So guys, there are many details about this architecture, which I'm not going to get into the details of, but please follow the sources that I'm going to provide today. The first one. In the first hour, I've talked about the recurrent model of attention. Then in the second hour, I've talked about the transformer-based attention, which is not recurrent at all. It is calculated in different types with a multi-headed attention mechanism. And they're both called attention. Totally different mathematical functions, both called attention. I strongly recommend you read this article, Attention and its Different Forms. Okay? Why they are both called attention? What are the similarities? What are the different things? Because the attention in the transformer is mathematically very different than the attention of the recurrent attention model of attention in Badanu's encoder-decoder architecture. But they are called attention, and actually they have a causal relation. I mean, that attention model caused these guys to come up with the idea of transformers. And second, this guy, remember this guy, the fantastic YouTube video that made us understand the LSTM video. He has done a significant video for LSTMs, transformers as well. Step by step, the guy explains every part, the positional encoder, then how does the encoder works, what does the encoder do, what does the self-encoding mechanism does. Fantastic business, please watch it. And then after watching it, read the paper. Then you'll be ready to use transformers in your projects, okay? Plus, there are many applications of transformers, guys. Actually, today, that GPT-3 is a transformer decoder-based generative model. A generative model is added to it. It's using the architecture of the transformer decoder so that it can create new words and text. And actually, the BERT, bidirectional encoder representations from transformers, is a fantastic transformer encoder-based architecture, which Google or Amazon uses for their searches. So if you're trying to carry a text to a high representation to create something, for example, from that representation, you are going to draw an image. You definitely need a transformer encoder, guys. And next week, I'm going to talk about transformer and vision transformers in the next week. So that will be the stuff of the next week. So before I finish, many suggested reading this week. Okay. And again, before I finish, not much time left for the projects. So I've got only one lecture. Next week, we've got the Bayram. The other week, I'm going to talk about vision transformers and some RNN trackers, multi-target trackers. So before that, seeing this lecture, I think you are ready to decide on your project because you now have information about recurrent model of attention plus the transformers. So if you're doing some stuff on text, maybe you could use these architectures. If you're doing some stuff on text plus image, you could combine different architectures. You can combine different models and try fantastic things. So I think we are at a point at which we are ready to definitely decide our project. And as promised the previous week, I promised, but I forgot. I'm going to open the project proposals page. And I'm waiting for you guys to upload your project ideas the next week until the next lecture. So that in the final week before the presentations, at least we'll have an idea to discuss. We'll have some time to discuss your ideas. Okay, any questions about transformers?